So today we'll start with the dropping mercury electrode. We have last class we have talked about the introduction to different polarographic methods, and now we will study the dropping mercury electrode in details. So dropping mercury electrode is a small polarizable electrode. It is produced by passing a stream of mercury through a resistance glass of a very fine capillary, and the internal diameter of this capillary, it typically ranges in 5 to 9 centimeter long. So the mercury drop, it falls at a steady rate of 3 to 5 seconds per drop, and it is adjusted. We can also adjust it, the mercury drop. The current oscillates between a near zero value as the drop falls from the capillary to the maximum value as the surface area of the new drop increases. So what is the advantages of this dropping mercury electrode? The first is the surface area is reproducible with a given capillary. Then the constant renewal of the electrode surface eliminates passivity or poisoning effects. The large hydrogen overpotential on mercury, it renders possible the deposition of substances difficult to reduce, such as aluminium ion and manganese 2 ion. Mercury forms amalgams with different metals, almost all metals. The diffusion current, it assumes a steady value, and it assumes a steady value immediately and is reproducible in nature. The surface area of the electrode, it can be calculated from the weight of the drops. So these are some of the advantages or the merits of using the DME, that is the dropping mercury electrode. Then the dropping mercury electrode is useful over the range of plus zero point 0.3 to minus 2 volt versus the standard calomel electrode. So above plus zero point 0.0 volt, the mercury dissolves and it gives an anodic wave due to the oxidation of the mercury ion. At potentials that is more negative than minus 1.8 volt versus SCE, the hydrogen evolution, it occurs in acid solution, and at minus 2 volt, the supporting electrolytes of the alkali, they begin to discharge. That is why the best range for the dropping mercury electrode to work is like 0 0.3 volt to minus 2 volt. So figure 8.2, here it shows the current oscillation with DME. This is the average response of the CV curve. Then coming to migration and limiting currents. The limiting current obtained when the mercury drop electrode is caused by the extreme state of concentration polarization, which results from the depletion of the concentration of the electrode substance at the surface of the electrode by the electrode reaction. The reducible or oxidizable ions, they are supplied to the depleted region at the electrode by two surface forces. The first is the diffusive force, which is proportional to the concentration gradient at the surface of the electrode, and second is the electrical force, that is proportional to the potential difference between the surface and the solution. So the limiting current, it can be regarded as the summation of diffusion current and the migration current. Now coming to what is this, the migration current? So the migration current is due to the migration of reducible or oxidizable ions, which is proportional to the electrical potential gradient at the electrode due to the forces of attraction. Unless this potential gradient is removed, the limiting current cannot be proportional to the concentration of the ions in the solution. So this migration current is eliminated by adding excess of the supporting electrolyte. Now what are the common supporting electrolytes that are used? They are mostly potassium or sodium salts. The potassium salts, they cannot be discharged at cathode until the impressed voltage, it becomes very large. The ions cannot be discharged at the cathode until it becomes very large. The large number of potassium ions, therefore, they remain as a crowd between the electrode surface. So there is no longer an electrostatic attraction that is operative to attract other reducible ions. So under these circumstances, the limiting current, it is solely controlled by the diffusion of the electroactive species through the concentration gradient which is adjacent to the electrode. So the migration current, it depends on the transference number of the reducible and oxidizable ion in the solution and the total current, that is Im, which represents the migration current, is equal to Ti and I1, where Ti, it represents the transference number of the respective ion, and I1, it represents the limiting current. So here in table 8.1, we can see the limiting current in solutions containing various concentrations of supporting electrolyte. Like for example, we have for KNO3 in molar, if it is 0 molar, then the transference number of lead plus, it is 0.77, and the limiting current that has been observed here is 17 microamperes. So if the concentration of KMnO4 is reduced to 1 molar, then the transference number for the lead ions, it becomes very slow, very less, and the limiting current is also reduced to 8.45 microamperes. So if we look carefully into this table 1, we see 8.1, we see that the transference number of an ion, it becomes almost practically, it becomes 0 in presence of 1 molar of KNO3 solution. So in such solutions, almost all the current is carried through the cell by the potassium and nitrate ions. However, these are not reduced before the evolution of hydrogen, and so the reduction of the lead ions, they remain the only process by which electrons can be transferred across the interface between the electrode and the solution. So in this, by this way, the migration current is eliminated by keeping the supporting electrolyte 50 to 100 times higher the concentration of the reducible ion. Then coming to diffusion and residual currents. So what is diffusion current? So in the presence of excess of supporting electrolyte, the electrical force on the reducible or oxidizable ions is nullified, and therefore the limiting current is solely the diffusion current. So Ilkovic, he explained examined the various factors which govern the diffusion current and deduced a theoretical equation as ID is equal to 607 N C capital D to the power half, M to the power 2 by 3, and T to the power 1 by 6. Here ID is the diffusion current, small n is the number of the electrons that takes place in the electrochemical reaction, D is the diffusion coefficient, C is the concentration of the electroactive species, M is the rate of the flow of the mercury drop, and T is the number of drops of mercury in seconds. So here we have a constant in this equation, we have a constant that is 607. Now this 607, it arises as a result of the combination of various other constants that is present in the equation, including the value of Faraday. Now if we look into 8 figure equation 8.3, keeping all the factors constant, we see that the diffusion current ID is directly proportional to C. That is, there is a linear dependence of the diffusion current upon the concentration, keeping all other factors constant. Now this particular inference, it is very useful in quantitative polarographic analysis. Now in practice, the limiting current is not exactly the diffusion current. The supporting electrolyte, which is 50 to 100 times that of the electroactive substance, it contains impurities which may contribute a small current in addition to non-Faraday condenser current, which is called as the residual current. So now again let us define what is this residual current. So even in the absence of a electroactive substance, there are other a small amount of current is always present in the solution. So this particular very little amount of current is referred to as the residual current. Now theoretically or technically speaking, the residual current, it consists of two components. The first is the reduction of trace impurities that is present in the large concentration of the supporting electrolyte used. These include dissolved oxygen, traces of metal ions such as ferric iron, lead, and arsenic. Out of these, the dissolved oxygen can be removed by passing pure nitrogen for 10 to 15 minutes before taking the CV curve. The second source is the charging component current or capacitive current which is non-Faraday, and it is present whenever the working electrode potential changes. Mercury is unique in remaining electrically uncharged when it is dropping freely into the supporting electrolyte. So the small current that is observed from the supporting electrolyte system is because of the continuous charging of the new mercury drop to the applied potential in order to remain neutral. The mercury is covered with an electrical double layer of positively and negatively charged ions of the electrolyte. The capacity of the double layer and hence the charging current it vary depending on the potential which is imposed upon mercury. So this is the in figure here 8.3 you can see the residual current for a zero point 0.1 molar solution of HCl. So this residual current is responsible for determining the accuracy and sensitivity of a method at low concentrations of electroactive species below 10 to the power minus 5 4 molar. So concentrations around 10 to the power minus 5 molar of electroactive species, the residual current is larger than the Faraday current of the substance to be determined, and therefore it is not sensitive. So the residual current it has to be compensated at the potential at which the diffusion current is measured. So now coming to the different factors that influence the diffusion current. So the Ilkovic equation is important because it shows the direct relationship between the diffusion current and the concentration of the electroactive substance. It also accounts for many factors which influence the diffusion current, and these factors are the concentration of the electroactive substance, the dimensions of the capillary, and the pressure on the dropping mercury, temperature, the viscosity of the medium, and the composition of the base electrolyte, etc. So first we'll start with the concentration of the electroactive substance. So from the Ilkovic equation, we know that ID is directly proportional to C, or ID can be written as K into C, where K is the proportionality constant, or overall we can say ID by C is equal to constant, keeping all the other factors constant. So this is the basis of the quantitative polarographic analysis. But there are certain observations have been made where ID by C does not remain constant, and the current is determined by the rate of the chemical reaction and sometimes the adsorption of the electroactive substance or its electrode reaction product. Then the second factor is the capillary characteristics and the factors affecting them. From the Ilkovic equation, it is seen that the diffusion current depends on M and T, which are together, they are called as the capillary characteristics, and therefore they are affected by the variations. The M is directly proportional and T is inversely proportional to the net pressure on the mercury drop. So these effects are reported in terms of height of mercury column above the capillary tip. Accordingly, we have m2 to the power 3 into t1 to the power 1 by 6 is proportional to root h and id of the Ilkovic equation. So that is, putting all the values, substituting, we see that id by root h is equal to k dash. So any deviation from this indicates that the current must be partly or wholly governed by the rate of some processes other than diffusion of the electroactive substance to the electrode surface. So here in table 8.2, we can see the effect of mercury of pressure on M and T. So here, when the height of mercury column is 100, the M is 4.2, time is 1.75, so MT is now is 7.48, and the height corresponding in centimeter is 106. Then for when the height is 27, the M has been given to be 1.0188, and T is the time required is 7.37, the MT becomes 7.46, and the H is 25. So this is how this is the data for the when we use zero point 0.1 molar potassium nitrate, and the data has been plotted shown for minus 1 volt versus the CSE. So this is the effect of mercury pressure on different parameters. Then coming to the effect of temperature on the diffusion current. So The change in temperature, it affects all the values of the Ilkovic equation except the value of n, that is the number of electrons that is involved in the reaction. The temperature coefficient of m, it's about plus 2.7% per degree, while that of T is about minus 0.222% per degree. So the temperature coefficient, that is m2 to the power 3, m to the power 2 by 3 into T to the power 1 by 6 is about 0.15% per degree. So here we can see that the temperature coefficient of the equivalent conductance, and therefore the diffusion coefficient is close to 0.02% of the C4 solutions. In addition, the numerical constant 607 is also affected, and the temperature coefficient of this range becomes all this. So combining the above information, we can see that the temperature constant should be remain within plus minus zero point 0.5 degree. Then the influence of the solvent and the supporting electrolyte on the diffusion current. So the diffusion current, it depends on D of the electroactive species, which in turn depends on the viscosity. So the diffusion current decreases with increase in velocity of the solution, as D is inversely proportional. So as we are discussing, the changes in the composition of the supporting electrolyte by adding complexing ligands to the electrolyte solution also changes the size of the metal complex, and therefore D of the ion. The ID decreases with complexation and the E half shifts to the more negative potentials. It is therefore necessary to keep the concentration of every constituent of the supporting electrolyte constant with about 10% accuracy to n plus minus 10% to ensure the variation of ID it resulting from this effect will be very small. So this is the about all about the various factors that influence the ID. Then coming to the polarographic equation. So what is the generalized polarographic equation? So let us take a general electrode reaction in which any process of the reduction at the cathode is accompanied by a simultaneous oxidation, as free electrons cannot exist in solution. That is, the oxidant plus n number of electrons, it gives rise to the reductant. So the cell potential reaction for this reversible reaction can be given as E is equal to E0 plus RT by NF, ln of activity of the oxidant by activity of the reductant. Then we can write, using the Nernst equation, we can write E is equal to E0 plus 0.059 by N log of concentration of the oxidant by concentration of the reductant in their standard states. So now here we have used the subscript O to denote that they are present at the electrode solution interface. Now before the commencement of the polarographic process, only a small residual current flows and the concentration of the electroactive material is same in the entire solution. So as soon as the applied EMF it exceeds the decomposition potential of the electroactive material, some of the reducible substance at the electrode solution interface it is reduced and its concentration begins to decrease. Since there is a concentration gradient that has developed between the concentration of the substance at the interface and between the bulk of the solution, then as a result of this, the ions will start moving from the higher concentration to lower concentration, that is from the bulk of the solution to the interface of the diffusion. Then the current observed it depends upon the rate of the diffusion of oxidant, and it is given as by simple I is equal to K1 into concentration of oxidant minus concentration of oxidant at the interface, that is OX0. So that according to Ilkovic equation, we know the value of K1 which is equal to 607 N of oxidant D of oxidant to the power half, M raised to the power 2 by 3 and T raised to the power 1 by 6. So this is the directly we have applied the value of I which is equal to the Ilkovic equation. Now when the current it attains the limiting value that is represented by the diffusion current plateau, the concentration of the oxidant at the electrode solution it will becomes 0. And now what happens it is the I it now changes to K1 into oxidant only, because the oxidant 0 it has become equal to 1. So this is Ki K1 into concentration of oxidant is equal to ID. So comparing the both the above equations, we see that OX0, that is the oxidant concentration 0, is equal to ID minus I by K1. So if the metal ion, that is the oxidant, is reduced to the metal, then most of the reductant they forms amalgam with mercury, because we know that almost all metals they are very prone to form amalgam with mercury. So similarly, the metal that is used here it also tries to form an amalgam with the mercury drop. Thus the concentration of the reductant formed is proportional to the absorbed current, that is I is equal to K2 into reductant 0, where K2 has the usual Ilkovic value equation value. So if the reductant is soluble in water, it will diffuse from the surface of the electrode to the bulk of the solution. So the concentration of the reductant 0 at the surface at any value of I will be proportional to the rate of diffusion of the reductant from the surface of the electrode. So we see that the same equation also it applies to the reductant. Then substituting all these value in equation 8.6, we see that E becomes with E0 minus 0.059 by N log of K1 by K2 minus 0.059 by N into log of I by ID minus 1. So when the potential of the dropping electrode is equal to half-wave potential that we represented as I half, then I is equal to ID by 2. Then the overall equation, this 8.11, it now it can be written as E is equal to E half minus 0.0591 by N log of I by ID minus 1. This equation is called as the polarographic wave equation. This is the generalized form of the polarographic wave equation, and it represents the potential as a function of the varying current at any point on the polarographic wave. The theoretical statement here it is similar to that of the above. So this is the generalized equation, or we call it as the equation of the polarographic wave. So this follows for all the numericals that are related to the process of polarography. So now coming to E half and the effect of complexing agents. So what is E half and why is it necessary? So E half is the half wave potential. The electroactive material in polarography is characterized by its half wave potential, that is E half. So under any defined set of conditions, each substance has its own characteristic E half, and this is the basis of qualitative polarographic analysis. The half wave potential is defined as the potential at which the current due to the reduction or oxidation of the substance responsible for the wave is half as large of the plateau, like that is shown in figure 8.4a and b. So this, the halfway potential here, it is clearly defined. So before reaching the value, what is the half value? The before the substance forms a plateau, then the half of the potential that is required, it is called as the halfway potential. Then coming to the effect of complexing agents. So in the case of complexation of metal ion with the complexing agent, the electrode reaction, it proceeds in two steps, that is shown here in figure equation 8.14 and 8.15. So the expression for the electrode potential for such a system, here we can write it as E half is equal to E 0 plus 0.591 by n log of k in step minus 0.05915 by n into log of x minus b. Here it has been shown. So where p is the coordination number of the complex formed and xb minus is the complexing agents. So if we plot the graph, if the graph is plotted between log x that is taken in the x-axis and e half we have taken, then a line with the slope equivalent to this value will be obtained here as it has been shown. And we can see the value of p, that is p is the coordination number of the complex, it can be determined from the plot. So once we know the p, that is the coordination number, then the instab that you have written here is the instability constant of the complex ion can be determined using equation 8.17. So this is how the E half value can be used to know the instability complex of a coordination compound. The shift of E half of metal ion by complexation is useful for quantitative analysis of samples containing more than one metal ion to eliminate interfering effect of one metal ion upon another, or to promote separation of E half of metal ions in a mixture for simultaneous determinations. So the E half values of few metal ions in complexing and non-complexing medium at the dropping mercury electrode, it has been shown here in this table. Suppose the ion is Cd2 plus, that is cadmium 2 plus. The non-complexing media is minus 0.59 volts. For 1 molar HCl, it is the E half value is minus 1.1 volt. If we employ 1 molar KCN, it is minus 0.64 volt. And if we use 1 molar NH3 and NH4Cl, then the E half value is minus 0.81 volt. So here we can see how the E half value for a particular ion in complexing and non-complexing medium, it changes and it is highly dependent on the nature of the medium that is used. So now coming to determination of N and reversibility. So it follows from equation 8.13 that when a plot of log of I by id minus I is plotted against the corresponding potential of the electrode on the raising portion of the wave, a straight line is obtained. The slope of this line, it will be equal to 0.059 by n, from which the n can be determined. Now, if the n is an integer value, then we can conclude the electrode reaction responsible for this wave is reversible in nature. So, if the slope of the log plot is larger than the expected or n is not an integer, then we can say that the wave is irreversible or is a proof of the existence of some new slow step processes. So here, this is figure 7.5. Here we can see the log plot of cadmium 2 in 1 molar HCl. This is how it looks like. The half wave potential for reversible wave is easily found from a log plot by interpolation to find the value of the potential where the log term is 0, that is in figure 8.6. So another method to determine the reversibility of electrode reaction, which is very simple and rapid, is measuring the potential corresponding to 1 by 4 and 3 by 4 from the polarogram. So first we will measure the E1 by 4 for the reversible cathodic wave, that is E1 by 4 is given by this formula, and then again we will find out E3 by 4, so which is given by this formula. Then E3 by 4 minus E1 by 4 gives us this value. Then altogether, using substituting, therefore the value comes to be minus 56.4 by n into mv, and for a reversible anodic wave it is equal to plus 56.4 by n mv. So the irreversible reactions, many electrode reactions are partially or totally irreversible, that is O plus Ne forming R. The polarigram obtained in such cases is drawn out and less well defined. The polarographic equations for such reaction is E is equal to E half minus 0.0591 by alpha into n into log of I by id minus 1, where alpha is the transfer coefficient and it accounts for the kinetics of the electrode process. So even in such electrode processes, diffusion current is proportional to concentration and therefore can be used for quantitative analysis. However, the E half, it varies slightly with the concentration of the electroactive species in the solution. Then coming to currents which are other than the diffusion currents. So first is kinetic current. Some substance, they are not electroactive but made electroactive on chemical reactions. The products so formed by chemical change reactions, they undergo reduction or oxidation at DME. The height of the polarographic wave or current is determined by the rate of the chemical reaction that produces an electroactive substance in thin air of the solution and the around the mercury drop. The waves of this kind, they are called as kinetic waves, and the mechanism for this mechanism responsible may be written as Y to O. By the forward reaction, the rate constant is kf and the backward reaction is kb, then O plus n number of E minus forming the reductant. So here, the for example, diol does not undergo reaction at DME, but on conversion to aldehyde form is reducible, and the wave height, it reflects the rate of transformation of diol to aldehyde form. So the kinetic current that can be obtained is given by equation that is shown here in figure 8 in equation 8.20. So when the Ik is the average kinetic current during the life of the drop and D is the diffusion current. So the kinetic currents that are recognized from m raised to the power 2 by 3 into t raised to the power 2 by 3, which does not vary with the height of the mercury column above the capillary, and it is independent of h corresponding. So the kinetic currents are not much in practical, they are not of quantitative analysis because of the poor sensitivity. Also, there is a possibility of impurities that are present in solution which might alter the height of the kinetic wave. So, however, this kinetic wave, although they arise in the solution, they do not are much used in qualitative analysis. Then coming to catalytic currents. So when an electroactive substance is reduced at the electrode by normal process, that is O plus Ne forming R, and then and if the solution it contains another substance, that is Z, which is not electroactive or reduces at the more negative potential than O, then what happens is it may catalyze the back reaction, and the reagent produced and the reagent O is produced by the following mechanism, that is R plus Z, it forms O. Now, because of the regeneration of the electroactive substance, more and more O is reduced at the DME, and there is an increase in current, that is the catalytic current. So this process it continues until the applied potential is very much negative, corresponding to the limiting plateau of O. The average catalytic current over the life of a drop is given by this figure. So here it's shown by this equation IC here from equation 8.23. So for example, uh, vanadium in 5 state plus E minus, it forms vanadium plus 4. So if the solution contains a small amount of hydrogen peroxide, then V5 plus 5 is regenerated by oxidation of V plus 4. So, so the 8 into 10 to the power minus 7 molar of V5 in zero point 0.1 molar phosphate buffer at pH 9, it gives current which is few thousandths of a microampere. But the same concentration of V plus 5 in the presence of 0.007 hydrogen peroxide, it gives 18 microamperes of current. So we see how the how does the catalyst, or what are catalytic currents. So it is therefore of importance for determining exceedingly low concentrations of original electroactive substances. Therefore, catalytic currents, they are highly useful for trace analysis of transition metals like tungsten, vanadate, molybdate, titanium, tellurium, iron with oxidizing agents like nitrate, H2O2, chlorate, perchlorate, potassium iodate, and hydroxylamine, because the IC is proportional to the concentration of the electroactive substance. Now the catalytic currents, they are called as IC, and they are independent of H like kinetic currents. Then there are waves, we call them as the adsorption waves. So what are these adsorption waves? Some electroactive species or their products, due to electrooxidation on or reduction, they are adsorbed on the surface of mercury drop to and give adsorption waves. So in electrode reaction, that is O plus Ne forming R, if R is adsorbed, then the current obtained is a very small adsorption wave, and a single wave is obtained whose height is proportional to O. But after certain concentrations, when the surface of the drop is saturated with R, and the second wave is observed at a more negative potential, which is the normal wave. This normal wave represents the reduction of O to R. So from the time the normal wave appeared, the height of the adsorption wave remains constant. The total wave of first and second together is proportional to the concentration of O and is diffusion controlled. So if O is adsorbed and not R, then the normal wave appears on the positive side. So here adsorption waves, they are observed in solutions of thiols, organic mercurials, uracil, arsenic, etc. This is figure 8.28. It shows the polarigram of sodium propyl xanthate. The adsorption waves have been used to evaluate the area of adsorbed species using the given equation in 8.24, where A represents the area that is covered by the adsorbed molecule. Then is the polarographic maxima, that is maximum suppressors. The current voltage curves which are obtained with electroreducible ions at the DME, they are frequently distorted by increasing the current beyond the diffusion current value and rapidly decrease to the normal diffusion plateau. So this abnormal increase in current is referred to as maxima, and it vary in shape from sharp peaks to rounded humps. To measure the true diffusion currents, the maximum it must be eliminated. So this can be done by adding small amount of surface active agents like gelatin, disturbed triton X100, which forms an adsorbed layer on the mercury solution interface to prevent streaming movement of the diffusion layer. So gelatin is actually widely used for this purpose. So other we can also use a non-ionic detergent, that is triton X100 and methyl cellulose. So qualitative and quantitative polarographic analysis. The qualitative analysis of a sample is carried out by matching its E half with the tabulated values of the ions in the supporting electrolytes. It is also advisable to use the log plot for knowing the correct value of the E half. So the halfway potential of some common ions, it has been shown here. If the supporting electrolyte is 1 molar NH3 plus 1 molar HCl, then the E half for different ions such as cadmium 2, cobalt 2 plus, copper 2 plus, it has been shown here. Here in table 2, for 2 molar acetic acid and 2 molar ammonium acetate, the values have been shown here. So these are the various E half potentials that has been shown here. Here we can see in this table, this is the E half of some common anions that has been recorded. Then coming to quantitative polarographic analysis. So polarographic analysis can be used between 10 to the power minus 3 to 10 to the power minus 5 molar concentrations. If the solutions have more than one electroactive substance, and if their halfway potentials in a particular supporting electrolyte differ by about zero point 0.4 volt for a single charged ion and zero point 0.2 volt for a doubly charged ion, then they can be determined. So if the halfway potential of two ions are close, then various experimental devices can be employed. Like they include precipitation of one, that is for lead and zinc mixture. Lead may be removed as lead sulfate precipitate for the determination of zinc. Complexation means by adding complexing agent. E half of one of the ions may be shifted to more negative potential, thereby delta E half of ions become more. The Cu2 plus ions can be complexed by potassium cyanide, and therefore E half is shifted to more negative potential than lead or cadmium. So there are three methods which have been widely used in practice. In all these methods, oxygen is removed before the polarigram is recorded. The first one is the wave height concentration plot, or we call them as the calibration working plots. So the standard solutions of different concentrations of iron under investigation, they are prepared using the same supporting electrolyte and 0.005% maximum suppressor, and polarograms are drawn with the known concentration of ions. Wave heights of all known concentrations are noted down, and after making correction of residual current, a plot is drawn as a function of concentration. Keeping the supporting electrolyte and the gelatin as above, polarigram of the unknown is also recording, keeping the temperature at 25 degrees centigrade. The wave height of this unknown is referred to as the working curve, and the concentration is noted. Then the second method is the internal standard method. The polarigram of the unknown solution in a supporting electrolyte and gelatin is recorded, and to the same solution a standard or pilot ion is added in known amount, and the current voltage curve, that is the CV curve, is recorded. So here the only condition is that the delta E half of the pilot ion and the unknown should be differed by 0.4 volt. So the ratio of these two waves is compared with the ratios of known amounts of the two ions. Then the method of standard addition. The polarigram of the unknown is first recorded, and then a known amount of standard solution of the same ion is added and a second polarigram is taken. So the calculations for this have been given below. If ID is the wave height of the first polarigram of unknown solution of volume V and of concentration Cu, that is the unknown concentration is Cu. ID2 is the wave height of second polarigram after adding V for VmL of the standard solution of known concentration, that is Cs. Then according to Ilkovic equation, we can write ID1 is equal to K into Cu and ID2 is given by this. So by using the formula, we can find out the concentration of the unknown solution from equation 8.26. So this is how we can calculate by the three process by which we can quantitative polarographic analysis can be done. Now coming to the instrumentation of a polarography. So the basic apparatus here for a polarographic instrument, here it has been shown here in figure 8.11. So the commonly used polarographic cell, it has an external reference electrode and it is the hydrogen cell. It consists of two compartments, one containing the solution to be studied and the other containing the reference electrode. These compartments, they are separated by a cross member that is filled with 4% agar saturated KCl, which is held in place by a medium porosity sintered disc. The second compartment is the solution compartment into which the DME is inserted and has N2 outlet and inlet provision. This simple recording polarigram, it has a potentiometer P up to any by which any EMF up to 3 volts can be applied. So R is the pen recorder, V is the voltmeter. So this is the overall. Here is a digital photograph of the original polarograph. It has been shown here. Then coming to amperometric titrations. We'll just take a break of 5 minutes and again resume with amperometric titrations. So now we'll start with amperometric titrations. So similar to conductometric titrations, potentiometric titrations, we also have amperometric titrations. So these are amperometric titrations. Different types of amperometric titrations are there. So we'll discuss one by one. So according to Ilkovic equation, that is ID is directly proportional to C, all other factors remaining constant. So if some of the electroactive material in the solution it is removed by interaction with some other reagent, then the diffusion current will decrease proportionally. So here some common in figure 8.13, some common types of amperometric titration curves of individual substances. Here it has been shown in A, B, and A dash, B dash. You can see various types of CV plots. So these are the different types of CV plots that we can obtain depending on the nature of the reactions that is performed. So this is the fundamental principle of amperometric titrations or polarographic titrations. The diffusion current at an appropriate applied voltage is measured as a function of the volume of the titrating solution. The endpoint is the intersection of two lines giving the change of current before and after the equivalence point. The voltage applied at the beginning of the titration must be selected so that the diffusion current of the substance to be titrated of the reagent or both it is obtained. So for each titration, the applied voltage is selected between a particular value, as here it has been shown in the figures. So here in figure 8.13a, the electroactive material is being removed from the solution by precipitation or complex formation with an inactive titrant, and that potential applied. So, for example, PV2 plus versus oxalate or Zn2 plus versus EDTA. So, in figure 8.13b, the substance to be determined does not give diffusion current, but the titrant, that is the reagent, gives current at the applied potential. So, for example, sulfate ions titrated with Pb2 plus ions. So, as long as the substance is available to the titrant it reacts with the substance and the current remains zero. After the substance is completely removed by the reagent, the excess reagent it gives its diffusion current in proportional to the excess volume added. So we see a reverse L-shaped graph is obtained. In figure here you can see this is a reverse L-shaped graph here in figure B. Then in figure 8.13c, both the substance to be determined and the titrating reagent give diffusion currents at the potential selected. Then 8.13d, at the applied potential, substance gives anodic current and titrant gives the cathodic current. The titration cell, it is made up of Pyrex glass and it is three-necked in nature. The two the flat bottom flask into which a microburette dropping mercury, that is the electrode gas outlet tube for N2 with an additional N2 inlet. The cell is connected to a reference electrode in the form of an attachment with a sintered glass disc separating the titration cell and the RE. The general procedure is in known volume of the solution for estimation it is placed in the titration cell. Then the required amount of supporting electrolyte is added and the cell is connected to the terminals of the instrument. The dissolved oxygen is expelled by passing pure nitrogen gas for 10 to 15 minutes and the initial current is noted. The known volume of the reagent is added from a microburette. N2 is passed for 2 minutes and then it is stopped. The current and burette readings are both noted. This procedure is repeated until sufficient readings are obtained and the graph gives endpoint at the intersection. So, what are the some of the advantages of amperometry? So, the titration can usually be carried out rapidly since the endpoint is found graphically. If few current measurements at constant applied voltage before and after the endpoint, they are sufficient. The titrations can be carried out in cases in which the solubility relations are such that the potentiometric or visual indicator methods they are not reliable or they are unsatisfactory. For example, when the reaction product is markedly soluble, that is then the or appreciably hydrolyzed. This is because the readings near the equivalence point, they have no significance in amperometric titrations. Readings that are recording in regions where there is excess of titrant or reagent, then the point of intersection, it gives the lines of the equivalence point. A number of amperometric titrations, they can be carried out at dilutions of 10 to the power minus 4 molar order, at which visual or potentiometric titrations, they can no longer yield accurate results. The foreign salts or the impurities may frequently be present without interference, and are indeed usually they are as the supporting electrolyte in order to eliminate the migration current, which is not possible in case of conductometric titration. The results of the titration, they are independent of the characteristics of the capillary. The temperature need not be known provided it is kept constant during the titration. Although a polarograph is convenient as a means of applying the voltage to the cell, its use is not essential in amperometric titration. The constant applied voltage may be obtained with a simple potentiometric device. Then few examples of amperometric titration. So first is the determination of zinc with EDTA. The reagents required, they are 0.05 molar zinc ion solution, 0.01 molar EDTA solution, and cyclohydroxylamine. So the titrant should be made 10 times stronger than the ion taken in a cell. First, the procedure is we take 5 ml of zinc ion solution in the titration cell, add 1 ml of cyclohexylamine and 19 ml of distilled water, and set the applied potential at minus 1.4 volt versus SC corresponding to Zn2 plus. The solution should be deaerated and titrated with standard EDTA solutions. Then we will pass nitrogen for 1 minute, then take readings of both burette and the galvanometer. So large initial current will be decreased as the titration proceeds to a very small value at the equivalence point and remains constant beyond the equivalence point. So the volume correction should be made and the readings should be plotted. The graph here, it should be similar to that here shown in figure 8.13a. Then coming to determination of sulfate with lead nitrate solution. So at the applied potential, that is minus 1.2 volt versus SCE, only Pb2 plus is reduced to give diffusion current and it is used as a titrant. The reagents required are zero point 0.1 molar anhydrous K2SO4 and zero point 0.1 molar lead nitrate solution, ethyl alcohol, concentrated HNO3, and thymol blue as the indicator solution. So what is the procedure for this process? So we'll take 25 ml of potassium sulfate into the titration cell. We'll add 2 to 3 drops of thymol blue indicator and few drops of concentrated HNO3 until a red color is obtained at pH 1.2. Now to this red color solution, we will add a few drops of 25 ml of ethyl alcohol, which will reduce the solubility of PbSO4 precipitate, which will which will reduce the solubility of the PbSO4 precipitate. Then the reaction here, it has been shown in equation, 8.27. So to this solution, we will pass nitrogen gas for 15 minutes to remove the dissolved oxygen, and then we will connect the DME and RE to the respective terminals of the polarograph. Then we will titrate with lead nitrate solution, that is added in small volumes, and pure N2 for 1 minute after each addition. So we'll note down the readings of the burette and galvanometer after stopping the passage of N2. Then the graph should be drawn between the volume of lead nitrate added and the current recorded from the galvanometer after making volume correction. So a reverse L-shaped curve will be obtained from which the end point is detected. Then the amount of sulfate present in the given solution, it can be calculated. Then coming to the determination of lead with standard dichromate solution. The potential selected is minus 1 volt versus SCE. with at which both lead ion and dichromate ions they give diffusion current. So the graph obtained will be V-shaped in nature. So the reagents are 0.001 molar lead nitrate, mm, 0.005 molar potassium dichromate, and 0.01 molar potassium nitrate. So the procedure is, we will take 25 ml of the lead nitrate solution and add 25 ml of the potassium nitrate solution as the supporting electrolyte and pass nitrogen for 50 minutes. We'll apply the -1 volt and make all the necessary connections. Then we will add the dichromate solution and pass N2. So after this, we will note down the readings. So initially the current due to lead 2 plus, it decreases as dichromate is added, and further it increases after the endpoint with excess dichromate. So we get a V-shaped graph, and then we can also do it with the unknown lead nitrate sample, and we can calculate the value of the lead. So now coming to titrations with rotating platinum electrode. So mercury cannot be used as an electrode at positive potentials because of its oxidation, and therefore rotating platinum electrode at 600 revolutions per minute it is used. So with platinum as the electrode, the attainment of steady state diffusion current is slow, and one has to wait for a considerable time after each addition of the reagent, and therefore platinum electrode is rotated. The construction of electrode is given below. So here is the rotating platinum electrode, or what we call it as the RPE. The determination of antimony with potassium bromide. So the reagents are 0.005 molar potassium antimonyl tartarate. 25 ml of this solution is diluted to 250 ml with 1 mHCl. Then standard potassium bromate solution is prepared in water. So we take 25 ml of antimony solution into the titration cell and titrate with KBr, potassium bromate, by setting the applied voltage. Then we will construct the graph accordingly and calculate the amount of antimony that is present in the solution. Then is coming to biamperometry or dead stop endpoint method. So in amperometry, we use one polarized electrode, which may be DME, or solid electrode or metallic electrode like platinum, and the other reference electrode that is non-polarized. So in this potential corresponding to the limiting current plateau is fixed, and I1 is measured as the function of the reagent value. So in the present method of biamperometry, a pair of identical metallic or solid microelectrodes, they are used. The method is very simple and used for the routine and automatic determination of a single species sample. Here the experimental setup for biamperometry, here it has been shown in figure 8.16. In this particularly 8.16 shows the instrumental setup. The instrumental setup is same as that of the amperometry, and the SC replaced with platinum electrode, and in the electrolysis cell only a magnetic stirrer is used. A fixed potential of 10 to 20 volt is millivolt is applied between the electrodes through the adjustment of resistance variable potentiometer. In such potential difference, one electrode will function as an anode, the other will act as the cathode. The shape of the titration curve, it depends on the reversibilities of the oxidation reduction couples at the electrodes of both sample. So two types of curves detecting the endpoints has been shown, 8.17, 8.18. Here it has been shown. If both couples involved in titration are reversible, we get curve of figure 8.17. At the end point, the current is zero near or near zero. For example, Fe plus 2 solution in sulfuric acid medium titrated with standard Ce4 solution, Fe2 gets oxidized to Fe3 here, and Ce4 it gets reduced to Ce plus 3. So if the potential difference between the applied to electrodes is about -2 volt, no current will follow. So here other examples are that can has been used is titration of adjobenzene in acidic solution with vanadium plus 2. So if one of the couples of the irreversible is irreversible, then the shape of the curve will be different. For example, titration of iodine by thiosulfate. So in this, The iodide iodine couple is reversible, and titrant thiosulfate tetrathiosulfate couple is irreversible. The titration curve here, it will be shown, the equation is shown here. When iodine in a solution containing iodide is titrated with thiosulfate, the anode will oxidize iodide and ion, and cathode will reduce the iodine, because iodide iodine couple is reversible in nature. So other examples are titration of azobenzene in dilute HCl with chromium ion. Then, in summary, these are the various what we have discussed. What is DME, the various applications, and the various amperometric titrations of DME. So these are some of the terminal questions that is associated with this chapter. With this, the part on polarography and amperometry, it is over. So we'll start with a new unit, that is applications of polarography, amperometric titrations, and voltammetry. So this is coming to the applications of polarography, amperometric titrations, and voltammetry. Uh, so some applications of polarography are, so here different samples and compound to be determined. They can be elements like copper, lead, tin, zinc. They can be identified in different types of foodstuffs by polarography. Even oxygen present in sea water and gases can be identified by polarography. The polarographic analysis of organic compounds. This technique is used in organic chemistry for qualitative and quantitative analysis and structural determinations. So, uh, most of the organic compounds, they are insoluble in pure aqueous medium and also in mercury to form amalgam. Therefore, the solvent in which the organic compound and its electrode product is soluble is added to the supporting electrolyte. The commonly used supporting electrolytes, they are easily mixed with organic solvents and various quaternary ammonium salts such as tertiary butyl ammonium iodide. Some of the organic functional groups that are reducible at the DME, it has been given in figure 9.2, table 9.2, it has been shown. Mhm. So here, the for these are some of the reducible organic functional groups. In addition, dibromides, aryl halides, alpha halogenated ketone or aryl methones, they can also be heterocyclic double bond, they reduce at DME. So it is also possible to convert the non-polarographic active groups into active polarographic groups and determine them. So if the functional group is carbonyl, we can use the reagent like GDT, semicarbazide, hydroxylamine, and then we can convert it to an active polarographic group, that is azobethene carbazide. If the organic functional group that is non-polarographic is primary amine, then Piperenal, CS2, and Cu3 copper phosphate suspension are the reagents, and using which they can be converted to azomethene, dithiocarbonate, copper 2 amine, which are all active polarographic groups. So it is also possible to convert non-active groups to active groups and then allow for their identification in polarography. Then coming to applications of amperometric titrations. So amperometric titrations, they have a wide range of applications. We know the Ilkovic equation, that is ID is directly proportional to C. So if some of the electroactive material is removed by complexation, then the diffusion current will decrease. So this is the fundamental principle of amperometric titrations. So some examples of amperometric titration: first is EDTA complexation, and many metallic species can be done, identified. Precipitation reactions using DMG, that is dimethyl glyoxime, lead nitrate, mercury nitrate, say silver nitrate, thorium nitrate, or potassium dichromate. It has been used for the identification of different types of ions, like DMG is used for Ni2 plus, lead nitrate is for sulfate and fluoride, mercuric nitrate can be used for identification of I minus, and likewise. So even oxidation reactions can be used, such as iodine oxidation reaction can be used for identification of sodium thiosulfate. Then potassium bromate or KBr can be used for identification of arsenic plus 3 and N2H4. Then substitution reactions, additions can be used for identification of alkene. So we see that amperometric titrations are particularly helpful in identification of a wide group of functional groups. Then coming to polarography experiments. So the determination of the nature of the ion, that is the E half. From polarographic experiments, the halfway potential of TL plus, it has been it can be shown. So the procedure is, we will take 10 ml of the zero point 0.5 millimolar solution of nitrate in zero point 0.1 molar KNO3 supporting electrolyte, and then we will draw the E half from the reduction and compare with the E value for the accurate E half plot. Then we can also, it is used for determination of cadmium that is present in unknown solution. So here, by using the calibration curve method and standard addition method, it can be done. Then what is the calibration plot method? The first, it involves the preparation of a stock solution of the cadmium. Then we will take the unknown solution and we will add KCl and gelatin solution, and then we will compare it with the calibration curve that we have previously obtained. So this is the calibration curve method. Then comes the method of standard addition. So here the polarograms, they are first recorded as under, and the second polarigram, it is recorded by adding a known amount. Then the second polarigram is obtained by this process, and hence by comparing we can find out the height and calculate the concentration. Then determination of lead and copper in carbon steel. So in the application of polarographic methods, of steel ferric iron, due to its reduction to near zero potential, they can also be identified. So other industrial important determinations for traces or minor constituents, like analysis of copper base alloys, analysis of high purity zinc alloys, and analysis of aluminum alloys, manganese alloys, and magnesium alloys, nickel alloys, analysis of metallic cadmium, and pure strontium salts. Then comes the determination of ascorbic acid, that is vitamin C, which is present in citrus juice, by the standard addition and calibration curve methods. So ascorbic acid, we know it is a very well known polarographic active substance, and it gives a very good polarographic identification curve. So using freshly prepared citrus juice, it can be done. The juice will be taken and we will add different amounts of buffer. Then the potent polarigram can be recorded, and then we will find out by comparing with the standard curve, we can find out. Then coming to applications of voltammetry. So all these techniques, they can be applied quantitatively for the analysis of a large variety of samples, like environmental samples, steels, etc. Pulse polarography, it's better for analyzing a wide range of inorganic organic analytes. The analysis of sample component is quite simple, and and any of the methods can be used. The amount of separation between these potentials will depend on the type of the potential difference. And here example has been given. This is the basic instrument of a polar voltmetry that we have seen. It consists of three electrode graph: the linear scan voltmeter, working electrode, reference electrode, counter electrode. The potential stat, it allows for the to impose the potential difference, and the computer attached to it, it measures the CV curve. So the practical methods, those are involved in voltmetry. First is the sample treatment, that is, it should always be taken in the solution form. Then addition of the supporting electrolyte, then bubbling of nitrogen through the solution, electrode cleaning, then addition of the standard electrolyte, measurement of the peak height, then calculation of the unknown concentration. Then coming to application of cyclic voltammetry. By far, cyclic voltammetry is one of the most versatile methods that can be ever be used in analytical chemistry. So what is this application of CV in coupled chemical reactions? So there are inorganic ions, metal complexes, and few organic compounds which undergo electron transfer reactions without the making or breaking of covalent bonds. Thus, the vast majority of electrochemical reactions involve an electron transfer step which leads to a species which rapidly reacts with the components via different types of chemical reactions. A cyclic voltammogram for the popular antibiotic chloramphenicol, here it has been shown in figure 9.2. This is the CV for chloramphenicol. It is a popular antibiotic. So we see there are three peaks that can be talked of: the peak A, the peak B, and the peak C. So these are the three peaks that has been obtained from the CV. So here peak A, it represents the initial reduction, peak B, oxidation, and peak C is the oxidation of the product resulting from the events of the peak B. So here these are some of the reactions that have been utilized in the formation of peak A, B, and C. Similarly, threonine is an ether which is conveniently be thought of representing the combination of the amino acid of tyrosine with hydroquine. So here this is in figure in you can see this is the tyrosine. So this is also it's oxidative CD. Here it has been the CD for tyrosine, you can see it has been shown here. So this is how the coupling reaction, the the redox reaction that is occurring in different molecules are identified by CV. So these are the some of the practical applications of polarography, amperometric titrations, and CV. So with this, we finish the chapter on applications. So this much for today. Next class, we will start with a new chapter.